All right, quick message from the management meeting, and that is on this Thursday will be test number 1. I start promptly at the top of the hour. If you come in late, you don't get extra time. I usually give everybody to the end of this class, and then maybe 1 or 2 minutes after that. If you've done the practice problems correctly, it should take about 35-40 minutes to do the test. I write my test, so you know the stuff you're going to finish early. Every problem on the test, I've discussed the concept behind that problem at least twice, a lot of times in class. There should be no surprises on the test number 1. All right, let me do something real quick, finish up the aromatic compounds, and then I'll go into the problem set for aromatic. I believe I went through Friedel-Crafts alkylation last week. I know I did. And now, listen carefully. I'm turning the switch. Will this be on test? To click off. And one other public service announcement, there's only one more shopping day till St. Valentine's Day. Wait tomorrow, I'm going to have my special St. Valentine's Day lecture. Whatever that means. All right. Polycyclic aromatic hydrocarbons. Real quick, poly means many, cyclic, ring. So that means rings that are connected together. You can have them in cycloalkanes. I just don't talk about it in this class, because you're not going to really see many of them in your daily life. I do, but anyways, in my life. And these are aromatic hydrocarbons with more than one ring. Again, switches off. Here's an example. Notice both rings are sharing 2 carbons. These are called fused rings or polycyclic. This is naphthalene. Naphthalene, again, you don't have to know the name or anything. That's the common, not the IUPAC name. And that's what mothballs are made of. Why moths don't like the smell of this, I have no idea. I'm an organic chemist. But when I was a kid, both my grandparents and parents had a closet filled with mothballs to keep the little stuff to keep the moths away from. I don't know if we had any, but they had them. That is moths. All right. Now, another important polycyclic aromatic compound is graphite. Graphite, think of it as large sheets of paper stacked on one another, like this is, which reminds me I better set this around. And think of sheets of aromatic compound. And graphite, because they're a sheet like this, I don't know, I think I mentioned it, but it's always good to mention it again, that Wikipedia, when it comes to organic chemistry, and chemistry in general, but specifically, I know for a fact, organic chemistry is so heavily policed by people like me that it's about 99% right all the time, this last couple of years. There's 2 things on my list I haven't had a chance to go in and correct. Anyways, think of sheets of paper. Each one of these series of 6-membered rings, sort of like chicken wire, and each one is an aromatic ring. They're stacked on top of each other. Now, one of the questions you should always ask in my class is, why am I learning this stuff? And besides the obvious reason you want to get a good grade because someone told you, yeah, take this class as a requirement is it's in your daily life. Well, graphite is used as a lubricant in your car and bearings and things like that because the sheets come off easily and lubricate between 2 metals. Now, any of you right now who are taking notes in pencil, what you're putting on the paper is sheets of graphite because lead pencils no longer contain lead. They haven't since the Roman times. At one time, they did use lead to mark paper or whatever they called it back then. I don't know my Latin that well, but anyways, like 0. But anyways, these are sheets that are used with a little clay to make the lead in your lead pencils. When you write, that's what you're reading, sheets of graphite on the paper. Now, about 1995, which is not that long ago, a chemist at, I think it was Rice University or University of Texas, Smalley, and a Japanese worker, organic chemist, whose name I can't remember, independently came and found a way by doing certain chemistry, you can take the sheets and bend them into tubes individually. And we call those nanotubes. And it turns out nanotubes, when put into other things, give things very strong properties, make things stronger, and have other properties that are quite good. Example would be if I could take plastic and make it as strong as metal, think of the advantages. You can make a car or a plane much lighter, better fuel economy, which is money. And if you save money, that's a good thing in business. Well, since 1995, 96, all the major governments in the world, United States, Germany, Japan, China, have been pumping billions of dollars into nanotube research. Now, back about 2010, give or take a year, these two, I think they were Swedish or somewhere in that area of the world, scientists discovered, because many people said the actual sheet, even though you can make it into two, you can't separate one sheet, which is called graphene. Well, these two scientists, they weren't chemists, I think they were physicists. They used crystallography techniques from chemistry and physics. Said, well, if I take a piece of graphite and take some Scotch tape and go like this and pull it off and dissolve the Scotch tape, could I pull off a sheet of graphene? And sure enough, they did. And guess what? They won the Nobel Prize in chemistry for that, which they deserve to do because they did something nobody thought you could do. And the governments in the world have been pumping in billions into that too because of the obvious advantages. Like I said, nanotubes, and that's that. All right. Again, that won't be on the test, but it's everyday important things going on. Researching graphene and nanotubes is hot and heavy right now throughout the world. All right, aromatic problem set. Over the weekend, no, I didn't suffer a miracle. I have a miracle, so my hearing's still bad. Remember, letters of the alphabet are the hardest thing for me to perceive, so say it clearly, but don't scream it. And I go through one page at a time. Let's see if I made any mistakes on the keys. Once in a while I do, and I have plenty of mistakes, I'll correct them. All right, first page. Give the UPAC name for the follower. Remember on Blackboard I have, and I sent out his email, the points breakdown. Are we still working?
Let's point out the ceiling.
All right, well, thank you.
You're welcome.
I'll have to put you down in the credits as an assist. Thank you. By the way, I'm learning names, so look out. Soon, all of you will no longer be anonymous students. All right. Let's look at the first page, and like I said on test one, I think about 45 to 47 points, one of those two numbers, will be nomenclature, one type of nomenclature question. Give the UPAC names for the following. Any questions? A, B, C? Is there a D down here? No, A, B, or C? Any questions? You do B? Of course I can. If we look at B, what do we see that's different? A ring with 3 double bonds that are conjugated, alternating single, double, etc. And, ooh, a methyl group on the ring. That's toluene. And then NO2 is nitro, so it's nitrotoluene. We have 1,2 disubstituted, which is ortho. Remember, this is only used for benzene rings, aromatic systems. Just to remind you, for dye substituted aromatic system, ortho 1,2 dye substituted, metal 1,3, para 1,4. Notice that's 1,2. Over here I have ethyl isopropyl, and therefore benzene ring 1,4 para ethyl isopropyl. Because I'm not holding you to the IUPAC alphabet rule. If you put para isopropyl ethyl benzene, I would have marked it correct. All right, when you have more than one, two, use numbering. And if we look at E, I have VR, Romo group. Remember, I asked you to learn the new table of new substituents. They have halogens, and VR is bromine, which is bromo. There are 3 of them, that's tri. Di is 2. I'll never ask tetra, which is 4. And all you in the front row have everybody behind you have said that. And therefore, tribromo, I need 3 numbers, and I can call 1, 1. This is 3, 5, doesn't matter which one I start as 1, it'll be the same. All right. The other type of nomenclature question is, draw the condensed structure for the following IUPAC name of molecules, and let me show you something that you should not do. Say in a test I put down benzene, you say, oh, I know what benzene is, and you write this. I'll give you 0 points. You come to me and say, well, shouldn't I get partial credit? And the answer is no, and always will be no. That's cyclohexane. It's like on an A&P test, if you said, draw a hand, and you drew a foot, should you get partial credit? Well, they both have digits. No, this is different. This is benzene. You can draw it this way. This is the other resonance form of the Kekula form, or even though I don't do it, you can draw it that way. I just think these 2 are cooler. But that's my personal opinion. Remember, benzene is aromatic with the double bonds in there, either showing the pi electrons or the actual double bonds. All right. I'm in the neighborhood, let's do B. And how do you decode this to know what to draw? You start from the right and go this way. And what do we have? Benzene, ring with 6 carbons, my double bonds. And I have ethyl chloro. And therefore I have a chloro group and an ethyl. How are they? They're para, 1, 4. I put the chloro there, the ethyl there. You could have put the ethyl there and the chloro there, and that would have been correct. Most of you didn't do this, but I could do it, and it would be the same thing. So all I'm doing is rotating the ring. And on this bright sunny morning when you're drawing this, how many bonds to carbon, class? 4. Let's do it again with feeling. How many bonds to carbon? 4. Thank you. And I've got it on videotape now. Speaking about videotape, the bottleneck right now is me getting software so I can edit it. I just sent in the help desk request and also copied the vice president of IT here, who's a great, really great guy, Dr. Courier. I've been working with media services and they were not too helpful. So that's why things have slowed down. I don't want them to edit it. All right. Notice I made a mistake on D. I forgot to dye. Sorry. But anyways, I corrected on the problem set. Let's do it while I'm there. It would be 1 ethyl 2,3 di-N-propyl benzene. You start from this side, benzene. I have 2 N-propyl groups, 3 carbons to the N carbon. Where are they? On carbon 2 and 3. Carbon 1 is the ethyl. There are other ways I could write that, but most of you will write it that way. Remember, 4 bonds to carbon. Question?
Can you go back to D on the other one? Because
all right, next question, yes. Look out, it's Dr. White's awful humor before Valentine's Day. All right, which one did you want? E right here?
D.
E like D.
Yeah, as a dog. Right
I told you I have a hard time with the letters of the alphabet. I'm going to hand out cards, and you bring your own letters of the alphabet on flashcards. All right, let's take a look at this. Question is, what's the IUPAC name for that? I see a benzene. That's my root name. I have a chloro group and a T-butyl group, or terp-butyl. Either one will work on the test. Terp-butyl being my favorite, now I'm happy. And what are the substitution? I can call this 1, and that's 2, that's 3, so it's 1, 3. Or this is 1, 2, 3, it doesn't matter which way you go. And if we look at, oh, someone nice put a chart up here. 1,3-di substituted meta. So it'd be meta terp-butyl chloro benzene. If you put meta chloro terp-butyl, now here's why I don't hold you to the IUPAC alphabet rules. The rules are prefixes are not counted when doing alphabet priority. Therefore, this is a B, that's a C. And that's why I'm not. Is that your question?
Yeah, so I can put chloro before.
That would be totally correct, and you have everybody around you as witness. I said that.
Thank you.
Thank you for your question. Yes, thank everybody for that question. All right. Any questions on E while I'm in the neighborhood? Going once, twice. All right. The other type of question you'll see on test number 1. See, I realize you can't read my mind, so I'm letting you know, and I've done that in blackboard, is reaction. There are 2 types of reaction questions. 1, give the organic product or products for the following. And the other one, there'll only be 1 question, give the starting material. Let's do this one. A or B? Well, since I've already told you I'm not going to spend the time teaching you directors, even though we will do a lab on that. There are only 2 questions I can give you for this, and I forgot to put the general reaction. A or B? Oh, I'm in the mood for A, so let's do that. And the question is, what's the product or products of the following? And you look at that, and you say, what do I do? What's different? Benzene ring? What's chlorine? Halogen gas, ooh, fair trihalide. For this one, I've only seen it as chlorine and bromine. I wonder if you can do it with fluorine or iodine, but these are the ones. What happens, you replace one of the hydrogens on the benzene ring. Remember, benzene undergoes electrophilic substitution, which I'll never ask you that name, but because you don't want to break the double bonds here and lose the stability, you just substitute hydrogens. Halogen is substituted, you get HX, but that's inorganic. My benzene ring was X, chlorine, and the only other one I could ask you on the test is that one. Yes?
Okay, so when I was doing these, I was having troubles trying to figure out why you only put 1 CL and 1 BR.
Because all you do is replace the hydrogen with 1 atom or group. So, because of valence electrons and the octet rule, this is impossible. You can't. Because there are too many bonds to chlorine, or one of these chlorines. Therefore, chlorine has 7 valence electrons, needs 1 more electron, which it shares its electron with the benzene. Another way of which there's a convention usually you put the cation first. That's why you use the that's why you need the catalyst, because it forms that electrophile, and then when the H comes off, it reacts with the extra chlorine to give HCl. Does that help?
Yeah, okay,
That's
so...
the only ways I can describe it. Remember, on a benzene ring, you're only going to replace a hydrogen. Therefore, it can only have 1 bond to that carbon, because it already has 3 other bonds. 1, 2, 3, and it's going to be bonded to something else. And that's the thing about electrophilic substitution. How you remember it, I'll let you figure that out. Those are 2 ways I remember it.
Okay, so last question. Whenever you see the Cl2 and Br2 with the Fe, it is always going to look like that no matter what, right?
Yep. I'll bet everything in my wallet, there's more than $1 in there, trust me. Including my credit cards, and they're not maxed out, because I don't keep a running balance other than what I do this month on my credit card, so it's my own personal thing. But always, that's the beauty of functional group chemistry. When I show you a reaction, that's what's going to happen. When you see a door, if you walk through a door, is it going to block you if the door is open? No, because you know when the door is always open, or you can't open it in a building, you can walk through it. Same thing, any one of these reactions, no matter what example I pick, that's what's going to happen. They're rare cases, but that's at my level PhD where you consider what I'm teaching you, the 1 examples I have, if you want in the lab, that's always going to happen. And you're going to do some of these in the lab to find out if Dr. White's lying to you. All right, let's continue on. Let's look at, I have a question.
Did you see?
Okay, I was about to, let me do this. Hold on. All right, if we look at C, D, and E, I'll go like this. And let's take a look at this. Now, first of all, just to remind you convention. Here I have a general chemical equation. And this tells you A reacts with B and C. You can write it that way. Organic chemists do, and I am one, and I do. Or you can write it this way. A and B react with C. Or there's a third way. You can also write it. Generally, I'm going to do these 2. And therefore, that's one thing you should be aware of. Now, let's do A. First thing you do is look at, well, what's the question? Give the organic product or products are the following. Next, you look at it and say, what's different? I do. Well, benzene ring. Is that all? No. A carbon with a halogen on it. And what is a carbon with a halogen on it? It's an alkyl halide, Rx. So what I'm really doing here is reacting this with this, and aluminum trichloride with catalyst. Therefore, this reacts with R is anything with carbons, X is my halogen, aluminum trichloride is AlX3. X is usually chlorine and bromine in this one. And you do that special thing, you make a carbon single bond. The carbon with the halogen is the carbon that is bonded to the benzene ring. It's electrophilic substitution. So you only replace the hydrogen. You don't break pi bonds in a benzene ring because you'll lose all that stability, and it won't. And therefore, what's our methyl? You get toluene. This is probably the most expensive way of making toluene. We get it from oil. We have a question. Yes, quick. Look out, I'm using names because I'm learning them.
The product also, it's toluene plus HCl. Is that where the chlorine goes?
If you put that out on a test, and if it helps you, fine. If you look at the problem, give the organic, and HCl, HBr, water, things like that are all inorganic. Remember I said, and I'll say it again, organic chemists are very biased, inorganic stuff. So if you want to put that down, if it helps you, go right ahead. I won't grade for it. You got everybody around you as witnesses. Plus it's videotaped now. All right. Oh, I have to. Let's do E because it's fun. And if we look at this, we have this plus this reacting with that. One day somebody's going to invent a whiteboard where you just put it up and it's all erases. But they haven't yet, so. And the question is, what's the organic product or product? And what I've been secretly doing, not too secretly because I've already told you that, I'm inoculating you against the organic chemistry instructor's trick on test. Put a big, scary molecule. So I did. And you look at this and say, what's different? Oh, benzene ring. What's this? Well, it's just carbons and hydrogens and carbon-carbon single bond. Ah, carbon with a halogen. Halogens are X. Can be chlorine or bromine for this reaction. And that's a bad habit I just started. And aluminum trihalide. What happens? Friedel-Crafts alkylation. If we look at this, what's my R group? And who's it asked me, does this happen every time you do it? Yes, it does. That's the strength, and I'll be quite honest, the beauty of learning functional group analysis or reactions, because whatever the R group is what's going to happen 99% of the time. And that's all in this class will be. So I have my benzene ring. I have my R group. The R group with the halogen is the carbon the benzene ring will bond to. What's my R group? Cyclopentane ring. Do we break carbon-carbon single bonds? No. So therefore, I have a cyclopentane ring. And Dr. White is having a good ring drawing day. And that's how you do it. It looks complex, but when you break it down into what's different, it's nothing more than that. How am I doing time? Oh, doing good. Time flies when you're having fun with aromatic compound. Did anybody happen to smell some cinnamon or eat something with cinnamon in it? Or how about vanilla? Anything with vanilla in it, like frosting, cookies, ice cream? You know, good stuff in life. And think about, ooh, that's got aromatic compounds. Anybody happen to look at a carrot or tomato and think it has double bonds in it? This is a hard group. I will not give up. I've got the rest of the semester to convince you to think about organic chemistry outside the classroom. All right, next two, let's do both of them. F, that is the general reaction. That's the only one I can ask on a test since I'm not doing directors. And you take sulfur trioxide, react with sulfur, sulfuric acid, and you put on a sulfonic acid group, SO3H. And you'll learn later in the semester, way later, that that reaction is important in making the key chemical, the main chemical that's used in laundry detergent. And the next one, nitration, HNO3, sulfuric acid, reacts with benzene. It's the only reaction I could ask on test to put an NO2 group. One of your colleagues emailed me this, and I saw it this morning. I figured I'd do it in class instead of answering the email. How come NO2 group is put on? Not NO3. This will not be on test, but this is the way to answer that question. So remember that's NO2, and that is nitric acid is this. I can draw it this way. Sulfuric acid is a proton donor. I'll just write it as H+. Remember, Bronsted-Lowry theories of acids and bases, and look out, I'm going to do what I always do. Acids, proton donor. Here, take my proton. Non-bonding electrons on oxygen attract the proton. Forms this intermediate. It loses water, which is a good leaving group. Any molecule that's stable can leave, and you form the nitronium ion. And in a couple weeks, you'll actually be doing this reaction and putting a nitro group on a benzene ring. You'll use bromobenzene. And therefore, the only reaction on the test I can ask you, benzene, nitric sulfuric acid, nitrobenzene. And that's the problem set. Any questions on the aromatic compound? Going once? Going twice? So did I tell you I used to go to auctions with my brother-in-law a lot? He'd go, especially when he had his company running, he'd go to these industrial auctions, and I picked up that habit. It was interesting because the first time I won, he said, keep your hands in your pocket, don't move, otherwise you're going to buy whatever they're bidding. And things, equipment they're bidding were going up to $100,000. So, it was exciting. All right. Tomorrow will be my world-famous review for the next test. Make sure you don't miss it because students say it really helps them, which is why I do it. All right, just a quick reminder in case you came in late. If your name's on this list, don't forget by Thursday, bring in a signed signature sheet. Tomorrow I'll bring some. Also tomorrow, weather and Dr. White permitting, I'm going to try and get here 45 minutes early. I think our classroom is open. And if you have any questions, come early, and I'll be here and I'll answer them. The only thing I don't answer for this class, I could, but I won't, is what's the meaning of life, because that's, well, it could be organic chemistry, but it's not. All right, we've done that. I've done that. If you notice, I'm pretty much right on schedule how things should go, which is good. We haven't had any snow days. All right, guess what time it is? It's new functional group time, new chapter time. One class here, every time I say like about 20 minutes before the lecture, guess what time it is? Students would start closing their notebooks and everything. I said, no, it's not end of the lecture. They thought it was. But now on my lectures, I never end early. I am time down. All right, new functional group time. So far, I've just talked about molecules that have carbon and hydrogen for the most part. We have the halogens, the nitrogen, nitro, and sulfur. But really, I just talked about molecules with carbon and hydrogen. Well, let's bring a new element into the picture, oxygen. Now, listen carefully. The material I'm talking about on alcohols today, and I'll probably get to it on Wednesday also, will not be on test number 1. It'll be on test number 2. So what's an alcohol? An alcohol is a molecule that has carbon and hydrogens, and one of the carbons has OH group, which is called the hydroxyl group. This is an alcohol. I think you've all heard that term before, and we'll learn about alcohols in this chapter. And now we get to the exciting part of the semester, where when you look at a molecule, you look for something different. What's not carbon, what's not hydrogen, should get your attention on, ooh, an oxygen. And with a hydrogen on it. And if we look at this molecule, what's different? Hydroxyl group. What functional group is it? Carbon with the hydroxyl group. This is an alcohol. Now, the next couple of chapters, like a lot of them, I'll be starting out, here's the new functional group, I'll introduce you to it. Everybody say hello to alcohol, that was nice. Anyways, I'll introduce you to them. And then I'll talk about the nomenclature, how do you name them? Both IUPAC and a lot of these functional groups have been around for eons, so they have common names that people still use. I'll teach you those key ones. And then I'll talk about where you find them in nature or in our everyday life. And then we'll go to the fun part. First, how do you make them? And then how do you react them? And I get to go into some amazing things you never thought I could get into. All right, so the question is, what's the IUPAC nomenclature rule for alcohols? Or another way of saying it, on a test, here's the structure, what's the IUPAC name? 3 points. And these are both skills that people working in organic chemistry should know. All right, so we look at this molecule and say, what's the IUPAC name for that? Remember, all slides up here are on Blackboard. And I look, what's different? Hydroxy group on a carbon, alcohol. First thing you do is find the longest chain, you've learned how to do that, that has the carbon with the hydroxyl group. Well, let's find out. 1, 2, 3, 4, 5. You name that as an alkane, pentane. But now, for an alcohol, the A at the ending of the longest chain, you drop the E at the end of it and replace it with OL. So I drop the pentane, the E, replace it with OL. Next, what you have to do is use the number to denote the carbon the hydroxyl group is on, and you start from the end of the chain that gives the hydroxyl group carbon the lowest number. Because functional group carbons always have priority, which means the lowest number. If I start from that end, it's on 2. 1, 2, 3, 4. Remember, this is still a part of the semester that you have to know how to count up to 10 and what numbers from 1 through 10 are larger and smaller than the other ones. I hope you all agree 2 is smaller than 4. So this is now 2 pentanol. I'm done. For rings, it's the same way you've learned about rings, and with the alcohols, you find the longest chain, or in this case, the ring with the carbon attached to the hydroxyl group. What's different? What kind of ring is this? Every bend in the line is a carbon, 5. That's a ring. Don't forget, on Thursday, rings start with cyclo, then pentane. Since it's an alcohol, drop the E, add OL. When it's the only carbon functional group in a molecule, that hydroxyl group will always be 1. You don't need a number. Also, when you have one functional group in a ring, that carbon will also always be 1, so you don't need a number. I'm done. And the rest of the IUPAC rules are followed, except hydroxyl group has priority in the numbering system. What that means is if you have, and there's this whole set of rules, many rules I'm not going to be teaching you, because I'm going to stick to in this class, and the ACS final does the same thing, except for some natural products which have common names that everybody uses. There'll only be one functional group. Like if there's an alcohol and a double bond, it has an ENE-OL ending, and the hydroxyl group has lower number than a double bond, but I'm not teaching you that. All right. And with that, I'm going to let you try this one on your own. See, Dr. White's going to share. I haven't really had a chance to share with you yet today. And therefore, the question is, what's the IUPAC name for the following? Hi, let's go take a look at this. First thing you do is look at what's different, what's not carbon, what's not, an oxygen, with a hydrogen, hydroxyl group. It's on a carbon, this is an alcohol. How many carbons in the longest chain? Well, let's find out. 1, 2, 3, 4. 1, 2, 3, 4, 5. Hopefully all agree 5 is larger than 4. Therefore, oh, I'm in a rut today. I'm gonna have to get out of that. Pentane. It's an alcohol, pentanol. Which carbon is it on? Well, if I start from this side, it's 1, 1, 2, 3, 4, 5. Hope you all agree 1 is smaller than 5. So it's 1 pentanol. Am I done? No. As soon as I say 1 pentanol, that's all supposed, oh, look, another one of my favorite groups, they've been nice to me, is isopropyl. 3 carbons, center carbons of the chain. It's on carbon, if this is 1, that better be 2. That's 2 isopropyl, 1 pentanol. And that's how you do it. And a question, another type of IUPAC, and I'll do this one as you know I'm going to share, is draw the structure of the following molecule. 3 points each. You'll find out Thursday, but I say 3 points all the time. And so how do you decode this and know what to draw? You start from this end, the right, and move to your left. OL ending. Alcohol. If that were an E, it would be octane. Octane is how many carbons? 8. Where is that alcohol on carbon number 3? Now, warning, not Will Robinson, but anyways, I just did a generation gap thing. Anyways, warning. I have learned, and Dr. White does not break good habits, I always write my functional groups toward the right side of a chain as opposed to the left. You can do it either way. Therefore, for alcohols, when we get into other ones, I'm going to start here, 1, 2, 3. You could also start 1, 2, 3 that way. I'm going to do it this way because this is my habit. And on carbon 3, I have my alcohol. On carbon 2, I have a T-butyl group. And since I know there are 4 bonds to carbon, I'm putting the rest of the hydrogens. Remember, it's your job, if I make a mistake, correct me. And there you go. And since you know I'm going to share, draw the structure for the following, and that would be 4-ethyl 2-decanol. For those of you who have lab tomorrow, don't forget to bring the lab that's due tomorrow. Also, don't forget to wear proper clothing, no open-toed shoes or anything like that. Don't forget to bring your safety goggles, your safety glasses, and don't forget your to-do list. I think I covered everything. Don't forget to show up too. And please, as always, be on time. For all of you having lab this week, exciting week. You're going to learn how to do a distillation. All right, let's take a look at this, because I think the lab, nope. The last hydrogens just went down. How do you decode this? You start from the right. OL ending, alcohol. If that were an E, decade, 10 carbons. Carbons. Where is the alcohol, the hydroxy group? Carbon 2. Going this way, ethyl group, 2 carbons. Where is that on carbon 4? And there we have 4 ethyl, 2 decanol. How am I doing time-wise? Oh, I got 20 seconds. When you can only have a hydroxy group on the first carbon, this is called ethanol. I'll talk about this interesting little molecule. It has profound effects on your brain and body. And with that, I'm going to let you out a little 2 seconds ago.